All right. So I asked you to do your homework for today, right? So what? You need assistance on one of the problems? Well, let's do this first. I'm going to start off class by putting a problem on the board, and then I'm going to come around and I'm going to take a look at your homework. Okay? I just want to see what you did. All right? So while I'm doing that, you work on this problem. All righty. Enjoy. I just want to see that you made an attempt. What's your last name? What's yours? What's your last name, sir? It's the problem I want you to get started on. I'm not looking for 100% completion, just that you try. Yeah. I wish we had an infinite amount of time to sit here and, spend an hour and 40 minutes to do two problems, but we've got to grind out. I'm only going to give us till 2 o'clock, maybe 1:50 to continue partial fractions, and I'm moving on. So for this problem, the first thing you do, polynomial over polynomial, right? Can't do or don't need to do long division, right? Because the degree of the denominator is bigger than the numerator. So now you're looking for factoring the denominator. And that does factor. It's a quadratic type. It factors to be x squared plus 4 times x squared plus 1. Right? That's what your denominator is. So my new integral is this. Whoa, holy moly. Wow, okay. Sorry. I'm just going to start this over. Okay, integral, and it was x cubed minus 2x squared plus x plus 1. And then it factored x squared plus 4, x squared minus 4. Or x squared plus 1, right? So that's it, right? Now, the factors in the denominator, the x squared plus 4 and the x squared minus 1, are what we call irreducible quadratic factors. That means you can't factor them any further, but they're quadratic. And in this class, the most we're ever going to be able to deal with is quadratic and linear. That's all we're going to talk about, factors in the denominator. So remember from last class that for each quadratic factor, we have to introduce something, right? So let me go ahead and write down over here I'm going to rewrite the whole thing. But I'm taking it out of the integral because this is where I start to do my work for the partial fraction decomposition. So what do I put for each linear factor? For each quadratic factor. Ax plus b over the quadratic factor. So I'm going to put ax plus b over the quadratic factor, which was x squared plus 4. And then plus another linear factor, which would be cx plus d over my other quadratic factor x squared plus 1. And now I have to try and play that game where I can figure out a, b, c, and d, right? So let's try and figure it out. Multiplying both sides by the LCD, the left side becomes just the numerator. Right side becomes ax plus b times the x squared plus 1, and then plus the cx plus d times the x squared plus 4. You can't kill anything off, can you? So you're going to have to use that other technique, which was to go ahead and just expand it all out. Did anybody find that function on their TI-89 that does it for them, that expands it all out, that does the partial fractions for them? Yeah? Okay, so I'm going to just multiply this out. It's going to be ax cubed. Yeah, no, I didn't find it. What are you talking about? Bx squared plus b plus cx cubed plus 4cx plus dx squared plus 4d. So that's just algebra, right? Manipulation there. Now I match up all my, let me see, my x cubes. Here's an x cubed, here's an x cubed. I'm going to grab my x squareds. There's an x squared, there's an x squared. My x terms, there's an x, and then everything else is a constant, right? So b and then 4d. And we're supposed to put them together and then factor out, right? Like put the like terms together. So left side is x cubed minus 2x squared plus x plus 1 equals, let's see, a plus c x cubed plus b plus d x squared. Let's see, where am I? X's plus a plus 4cx, then plus b plus 4d. Any questions on what I did there? I mean, if you did your homework, you probably kind of caught on to this already. If you didn't, then you might still be stuck in the phase of it. The what? Okay, so I have a 1 in front of x cubed. I'm going to match that up here, 1. And then I've got the b plus d. That's got to be my what? My negative 2 right there. And then I've got my a plus 4c. That's got to be a what? A 1 right there. And then the b plus 4d has got to be my 1. Like that. And that should be a system of equations. Should be 4 equations, 4 unknowns, right? Did anybody use Wolfram Alpha to do this? No? I was going to show y'all, but I mean, when it comes to a test, you're going to be with your calculator. So who didn't have the calculator? You still don't have it, right?
Well, I found out that my calculator can do it.
That one will, yeah.
But I got to figure out how to like set it up because I don't know if it'll do one that large. I think it will, but
Okay. Like a 4 by 4, yeah. Still no go? Okay. All right, so you write down a plus c equals what, 1, b plus d equals negative 2, a plus 4c equals 1, and finally b plus 4d equals 1. And I'm not going to do that. I'm just going to give you the answers, okay? I'm not going to go through. You could do it on your calculator, all right? Or maybe not. We need to get together and figure out something for you, all right? And then on yours, if it, yeah, so maybe a plan B we need to find for you. Okay. Let's see. No one wants to spend that much time doing that by hand. You should get A is 0, B is 1, C is 1, d is negative 3. So those are our constants, and that means we can go back up to the original integral and replace those. And that's way up here. So my original integral, here I go. My original integral becomes the a. It's going to be two pieces, right? It's the ax plus b, so 0x plus 1 over the first quadratic factor, which was the x squared plus 4, right? Plus the cx plus d all over the other factor, which was x squared plus 1 dx. Does everyone see that? Anyone have a question on that? That's just a, b, c, and d. Yes. Are they? According to, I solved it using Wolfram Alpha. Should be 4a plus c. I'm sorry, yeah, I wrote it down wrong. Thank you, yes. Check this, fix that 4a right there, and that should just be c. See, look at it right here. I'll highlight it so you can see it. Where did I mess it up?
You have a plus 4c all the way up. See a plus 4cx. C.
Maybe they put the factors opposite when they started. Instead of doing
Oh yeah, you know what? I did them different. No, this is my work. I did the A, B, C different. Shoot, I didn't realize that till just now. Okay, well then we have to do this because I know I've done all this work right. Right? This is all right. So then someone's gonna have to solve this for me. Or I can tell you what it is. Hold on, let me just fix this. 0. It's just opposite here. It should be 0 for C, and then 1 for D. C should be 1, and D should be negative 3. Thank you for pointing that out. Everyone got that? That's what I fixed. So change this in here. So we get x minus 3 here, and then this is 0x plus 1. I'm glad you caught that there, because that would have been a nightmare if you caught it later. Okay, is that all right, everyone? Everyone's okay with me going on? Now let's look at these two integrals separately. I have x minus 3 over x squared plus 4, right? dx. And then the other one is just what? Plus integral 1 over x squared plus 1 dx, isn't it? And
Make sure that's set up properly.
can I do what?
The A and the B are proper. Just trying to make sure that I'm tracking it.
What do you want me to do?
Our A, like AX plus B is over the right.
It is. It is now. It wasn't a second ago, but it is now.
Just want to make sure.
Yeah, it is. All right. Well, any ideas here?
is it going to the right arctangent?
Yeah, the second integral is arctangent. So that's good. What else?
Substitution on the first one?
Substitution, u would be x squared plus 1, yes? Or x squared plus 4. Yeah, but what about that minus 3 up top? How about this?
Yeah, you can split it into two. Pull the -3 out.
Yeah, I'll pull that negative 3 out, but I'm just going to go ahead and take that first integral and make it two integrals. I can do that, right? I can take that first integral here that has two terms in the numerator and put each term separated over the denominator. Why did I do that? Yeah, this one right here is going to be an arctan also, right? The second integral is going to be an arctan. Just pull the -3 out. And then this one's an arctan also. They're still a little different. They're not the same arctans, right? Yeah.
What do you mean they're not the same?
Well, because the bottom of this one is x, the second one is x squared plus 4. The other one is x squared plus 1.
But you still write arctangent?
But you're still, yeah, but look at the formula for arctangent. Go look at it. Because the formula is this. For arctangent, it's integral of 1 over, I don't know how they have it written there. It's like u squared plus a squared or something like that. du is equal to 1 over a arctangent of u over a plus c, right? Isn't that the formula?
Yeah.
Right? So for us, a, in the second integral, a is what? In the second integral, in this integral, the a is 2. And in the third integral, the a is 1. Do y'all see it? Right? 4 is our a squared, so a is 2. 1 is our a squared, so a is 1. Okay?
So now you just do the substitution for the first one, right?
Yeah, now on the first one, I'm going to do a substitution. All right, so substitution on that first one. I'm going to let u be equal to 2 x squared plus 4. du then is 2x dx. I'm off by how much? 2, so 1/2 du equals x dx. And so that new integral becomes 1/2 integral, what is it? du over u, or 1 over u du, right? And what's the antiderivative of 1 over u? Natural log u, right? So 1/2 natural log u, but what was u? X squared plus 4. So that's the answer to that first integral, which is up there. You can't see it now, but that first integral becomes that right there, 1/2 natural log x squared plus 4. Now the second integral that's up above here in the third one, we said were arctans. So let's try and get that second one. What's that second one become? You have to bring that -3 out. So 1 over 2, but then times the -3. So how about -3 over 2? Right? Arctangent of x over a, which is 2. So x over 2. And then the other one plus, this one's just the straight up. See, when a is 1, it's just 1 over a arctan of x over 1. So that's just arctan of x plus c. I didn't? Yep, I see it. Arctan right there. That should be it. What's got me kind of, I don't know, my mind's somewhere else right now because my pen, does this seem like really thick writing right now, like compared to before, or no? I changed my zoom and I think it messed something up, but it looks about the same as it's always looked? Okay. All right, so how do you feel about that one?
So is this enough work when we get to like this point, just because we're plugging into our calculator and stuff?
Is what enough work? Solving the system of equations? Yeah, just your calculator. Yes.
A little factoring. Do we have to show you our factoring?
Say again.
Do we have to show you the factoring? What we factored it or something?
No, if you can factor, yeah, I mean, I know the calculator will factor for you, so. Are you good? Okay. All right, next problem. I'll do, what was the problem? Let's see, number 21 or 19? Let's take a vote. On the homework? 21, let's see, show of hands, 21. All right, I think 21's going to win. What was 21? What was 21? Thank you.
7 plus 4 over x squared plus 4. This is long division.
All right. So for this one, the first step would be long division, right?
19 was easy for me. Long division should be, what the hell is that? Long division.
So I'm going to put x cubed plus 4. So I left some spots in there for my x squared and my x terms, right, that aren't visible there. And then x squared plus 4 goes out here. What do you multiply x by, or sorry, x squared by to get x cubed? X, so I need to put an x in here. I'll put it right here. And then multiply through, you should get x cubed plus 4x. Then you come through here and you subtract this row. Did I already tell everyone that I'm putting all the notes that I do as PDFs also?
Yes.
Okay.
So I got that one.
All right. So now go ahead and add straight down, and you'll have negative 4x plus 4, right? And that's where we stop, isn't it? Because the power on the x squared that we're dividing by is larger than the power of what we're trying to divide into. So what we'll have here is plus the remainder, negative 4x plus 4, all over the divisor x squared plus 4.
That's it.
Right? Okay, so back to the integral now. Integral, this becomes x plus negative 4x plus 4 over x squared plus 4 dx. Yeah. How about that first term in the integrand? Easy business right here. The x, antiderivative of x, right? We're okay. How about this second integral here, that second term? You could do partial fractions, couldn't you? But you could also do what we just did in the previous problem, couldn't you? You could split it into two integrals. So why don't I do that? I'm going to save myself some time. I'm going to have a 1/2 x squared here. That's the antiderivative of this. So I'm already doing the antiderivative there. Now watch me here. Minus 4 integral x over x squared plus 4 dx plus 4 integral 1 over x squared plus 4 dx. Is that all right? Do y'all see what I did there? The last integral, right? The last integral is going to be what? Arctan. The middle integral, substitution. So ... You can do the rest. I'm not going to go through it. Now, if you had done the partial fractions, that's probably what most of you did, right? And so where did you get stuck? Was it just the long division part of it, or where'd you get stuck?
It was literally the part where negative 4x plus 4 over x squared plus 4. I started doing that. Or
Yeah, see, check this out. Yeah, I see why you got stuck. Because look, if you take this, right, and you're saying, oh, I'm going to do partial fractions on that. And what I want to do is I want to turn negative 4x plus 4 over x squared plus 4. I want to turn that into an ax plus b, right, over x squared plus 4. You already have ax plus b. Look, you already have an a in front of an x and then a b by itself. So you're trying to turn it into something it already is, right? If you can get it to ax over b, then you should be able to split and then do what we're doing right now. So what happened? Did you just get, every time you tried to solve for a and b, you got back exactly? Okay. Okay. Does that make sense though, everyone? Is that okay? All right. I'm going to continue if you don't mind. All right, this problem that I'm about to do is just to show you that As before, there's different ways to attack a problem. So let's look at integral x over x squared plus 4x plus 13 dx. I'm just going to try and change my zoom here just to see what happens. See, I think that's more like what it's been in the past. See, I can get more on the screen this way too. Can everyone still see that though? That okay? No, I'm kidding. I'm gonna stick with that. All right, so we could use partial fractions, right? Do we have to do long division? No. Can you factor the denominator? No. So what you would do here, right, your normal approach to this would be to try and write x over x squared plus 4x plus 13, right? And you would try and write that as an ax plus b over x squared plus 4x plus 13, right? That's what you would think to do, right? But it's already there, isn't it? It's already in that form. What's the a? 1. And what's b? 0, right? So you already have it there. So what do you do then? What do you do? If you say, let's do a substitution, right? U equals, let's try the whole denominator. Isn't the derivative of x squared plus 4x plus 13 going to be 2x plus 4? Do you have 2x plus 4 up there? Do you have 2x plus 4 over there? No, right? You have x dx? Now I heard solve for x, but the problem is where's an equation with x in it that you're going to be able to solve for? See what I'm saying? Like you don't have an x by itself that's going to be easy to get by itself, right? Does everyone see the challenge in this? You got to see the challenge before you can see how to attack it. Everyone see what's wrong? I mean, like, what do you do? Okay, here comes the sneaky business. It has to do with that. Remember that hidden 0? Okay, watch. Here's what I'm going to do. I'm going to take my original integral right here. What would I love to have in the numerator? I mean, what would I just absolutely love for this to have been? What? 2x plus 4, right? If my numerator was 2x plus 4, then wouldn't I had like du on top and u on the bottom? I would have been 1 over u du. So I'm going to make it 2x plus 4. I'm going to massage it until it becomes 2x plus 4. So the first thing I'm going to need is to make it a 2x, right? Yeah. But I can't just go in there and change x to 2x unless at the same time I do what? Divide by 2 also, right? So instead of dividing by 2, I'm going to multiply the front of the integral by 1/2. So that's the same problem, isn't it? So I've made the 2x appear. But I also need it to be a what? A plus 4. But I can't just add 4. If I add 4, I also have to subtract 4. Don't I? Now, here's what I've got. 1/2 integral 2x plus 4 over x squared plus 4x plus 13 dx plus 1/2 times negative 4 over x squared plus 4x plus 13 dx. So what did I do there? Split it into two integrals right here, right? I took my numerator, I split it right at the 2x plus 4. I took that part, put it over the denominator, and then I took the negative 4 over the denominator over there, and I kept the 1/2 in front of both of them, right? So I've just created two integrals. What do we know about this first integral? That's just going to be du over u, or 1 over u du, right? So the antiderivative of that will be 1/2 natural log of u, but what's u? X squared plus 4x plus 13. And then that's it, right? That's all I have for that one. Does everyone follow that? Okay. What about the other one, though?
Pull the negative 4 out.
Okay, take negative 4 out. That's fine. I'll write that. It comes what? Oh, minus 2. Integral 1 over x squared plus 4x plus 13 dx. Now, any questions up to this point? Because this is kind of critical time here. So, I have a rational function still, right? I can't factor the bottom. The bottom is quadratic. I don't want to go and try and turn it into ax plus b. Why? That's where I started the whole freaking problem, right? So I don't want to go back to that. I've taken care of part of the problem, haven't I? It's a little nicer than it was before. Okay, so this is, again, I'm showing you this because you need to see it. I'm going to look at the denominator here. I'm going to take this over here. I'm going to kind of stop my work for a second and come back to this. I'm going to take x squared plus 4x plus 13, and I'm going to complete the square. Do y'all remember how to complete the square? The technique for completing the square is to get it in descending order, which it is, highest power of x down, and then look at the term in front of the x, which is positive 4. You're supposed to take that positive 4, and we'll just call it b, is positive 4. Then you're supposed to take half of it. What's half of 4? 2. Then you're supposed to take that number, and you're supposed to square it, so you get 4. Does this ring a bell at all? It's okay if it doesn't. But so now what I do is I rewrite the problem, x squared plus 4x. And what I do is I take this last number that I got over here, this 4. Take that 4. And in my 0303 class, we call that the magic number. But this is Cal 2, so we're not going to call it the magic number, right? So that's the 4, right? We're going to take that 4. We are going to add and subtract the 4 at the same time, and then we still have the plus 13. Now, the reason why we do this is because if you follow that process, the first 3 terms are guaranteed to factor. It's a perfect square trinomial. Those first 3 terms factor to be what? X plus 2 squared, right? X plus 2 times x plus 2. If you FOIL those out, you get x squared plus 4x plus 4. But what's left still? Plus 13, but then the minus 4, so plus 9? Right? So I have transformed x squared plus 4x plus 13. I've transformed that thing up there, right, into this. Now, why is that a good thing? Let's see. If I write down that integral again, and I'm just writing this integral down, okay? I'm not going to mess around with the negative 2 or anything like that yet. I'll come back to that, all right? Just that integral. It's 1 over, but instead of all that x squared plus 4x minus 13, or plus 13, it's really what? X plus 2 squared plus 9 dx, right? Anybody have an idea of what formula we're going to be able to use for that? Arctan. If I do just a basic substitution right now, u is equal to x plus 2. Du is what? Dx. Then how could you rewrite that integral? 1 over u squared plus 9 du, which is 1/3 arctan of u over 3, right? But what's u? X plus 2. Bonus? Is that what you said? I wish. This is just part of this class, really. X plus 2 over 3. Yeah, nothing I showed you here is like, hey, and here's an advanced problem for you. No, this is middle of the road stuff here. Okay? The algebra never stops. It slows up a little in Cal 3, the algebra.
That's just because the calculus picks up.
Yeah, we make up for it by making you have to visualize things three-dimensionally. Okay, are we ready for a final answer? Because way back up here, I had a -2 in front of that integral, and then I had that 1/2 natural log stuff. So, final answer to this problem. Here we go, on the bottom here. The final answer, I'm going to write the original problem. Integral x over x squared plus 4x plus 13 dx is equal to, it was 1/2 natural log x squared plus 4x plus 13. Then my new integral, that my new answer, but the -2 in front of it. So -2/3 inverse tangent of x plus 2 over 3 plus c. Moral of the story is, if you ever have your rational function where you can't factor it, or when you look over there and you're trying to get ax plus b over whatever and you already have it in that form, you're going to have to do something. And the trick of seeing something and making it appear and all that, it's just one of our standard kind of tricks, okay? I'm trying to do 2 more examples. This one I'm going to do right now is going to go pretty quick. All right, so we have x to the 4th plus 3x squared plus 1 all over x to the 5th plus 5x cubed plus 5x dx. We have really no need for long division, right? Can you factor the denominator? You can pull an x out, right? And that's about it, right? And so even if you factor an x out, you're going to have an x to the 4th, aren't you? And I didn't show us how to do any of that with x to the 4th. Right? If it's linear, we put a number, right? A over whatever. But if it's quadratic, we do ax plus b over quadratic. If it's cubic, we didn't talk about it. So watch though. Watch. If I just make a basic substitution here, what's the derivative of that? 5x to the 4th plus 15x squared plus 5 dx. What do you have in the numerator? Yeah, you can factor a 5 out. 5, and you're left with x to the 4th plus 3x squared plus 1 dx, right? And then just divide both sides by 5, and you get 1/5 du equals x to the 4th. Wow. X to the 4th plus 3x squared plus 1 dx. So you have exactly there right? Exactly, the numerator is exactly 1/5 du, and the denominator is your u. So isn't this just 1/5 integral 1 over u du, which is 1/5 natural log of u plus c. But u is all that junk, right? So the answer is 1/5 natural log x to the 5th plus 5x cubed plus 5x. What's the moral of the story here? Yeah, don't bog yourself down. I mean, this is a problem that would be perfect for wasting your time, right? It's just perfect because you could get all tied up in long division and trying to do some crazy stuff and make things appear and not. This one was all ready for you. All you had to do was see something in its derivative there. This was a basic substitution problem disguised as a nasty rational function. Okay? So beware, be forewarned. Last one in this section. Maybe the last one. All right, this one I'm showing you because it's weird. All right, this one looks kind of tough. It's not even a rational function. It's not a polynomial divided by a polynomial. So you would think this doesn't even apply, like this section doesn't even apply to this, right? And there's not a whole lot else we have here. So I'm just gonna take a swing here, and my swing is gonna be just taking my cube root of x to be my u. I'm just gonna try a substitution and see what happens. What's du then? Well, remember, cube root of x is the same as x to the 1/3, right? So this will be 1/3 x to the negative 2/3 dx. Do you have that anywhere? I don't see it, right? Okay, so this is kind of a, I don't know, I'm kind of like, what the hell do I do, right? So let me do something a little different here. Let me make that same substitution, all right? But now before I take a derivative, I'm going to solve for x. So if I cube both sides, don't I get this? Right? If I cube both sides of that equation, u cubed equals x. Now take the derivative on both sides. What's the derivative of u cubed? U cubed. 3u squared du, right? Equals, what's the derivative of x? Dx. That's interesting, right? Look at this. What is dx for us in the problem? 3u squared du, right? 3u squared du. What's the cube root of x going to be for us? A u, right? Let me write the integral then. Are you saying that then it's 1 over 1 plus u 3u squared du? Is that what I'm trying to say? Yes? What? So ask. You sure?
So there's gonna be two U's, right?
Well, what I'm going to do is I'm going to wind up taking this 3u squared and I'm going to put it in the numerator of that fraction.
Yeah, 'cause that's what we're doing.
Yeah, I put it out there just to match it directly with the way it's written up here, right? You've got 1, 1. You've got 1 plus u, dx. This is all this, right? I'm just matching everything up. But now, that's just, wasn't that nice though? Wasn't that nice? Look at this. I'm going to take my 3 completely out of the integral. Integral of u squared over 1 plus u du, right? And now you have a polynomial divided by a polynomial, which is why this problem is in this section. So the first thing you would do is long division, and then you play the rest of the game. Okay, I'm not going to go through the rest of that problem.
So you do it all in U's, and then you come back to X?
Then at the very end, once you get your answer, you plug in what was x, or what was u, cube root of x. So there's a perfect example of an integral that looked like you would never even think of this section in the book, right? But it turned into it. And also, I'll point out, this part over here was a big deal. That's a big deal you should know about. If you ever make a substitution like u is like square root of x or cube root of x or any power of x, you can always raise both sides and then take the derivative. You can always do that. And it made it so much nicer to work with. All right. I lied. I said it was our last one. I said maybe one more. Well, for sure one more. I'm not going to work it all out. Same thing. I'm going to help get you set up and going on it. I just want you to look at that for a second. Just tell me, what does your instinct tell you to do here? Drop the class? I should bring drop slips. Drop slips? Anyone have drop slips? I don't even know if they have drop slips anymore. They do? They do. I brought some. Right? You brought one for everyone? That was very nice of you.
Replace R10
With?
the function of 1 over
X squared plus A squared.
That's the antiderivative. The antiderivative of 1 over x squared plus a squared is arctan.
X squared plus 1.
I don't know what you mean. Do we have a formula for arctan? Any other ideas? U substitution? What would you want your u to be? You want to do u is arctan x? Okay. What's du then? Or is that what you want now? The derivative of that? Du would be 1 over 1 plus x squared dx. I don't really see that over there. Maybe. You want me to keep going? I don't.
Show us a trig.
Into 2 integrals? No. Why not?
Multiplication.
Because it's multiplication. If there's multiplication. Well, yes. Integration by parts. Okay. U and dv are the two things you have to choose, right? Now, you don't have a whole lot of options here for your choice of u and dv. dv, you have to be able to integrate it to get it back up to v, right? There's only one thing here you're going to be able to integrate easily, and that's x. So x dx is your dv. Your u then is forced to be what? Arctangent of x. Du then, we just said, was 1 over 1 plus x squared dx. And what's the antiderivative of x to get back up to v? 1/2 x squared. But ultraviolet minus voodoo becomes 1/2 x squared arctangent, right? Arctangent x. That's ultraviolet, right? Y'all following me? Ultraviolet minus integral of voodoo. And what's my integral of voodoo? I can pull a 1/2 out, and it would be x squared over 1 plus x squared, wouldn't it? Dx. Y'all see what I did? And what could you do with x squared over 1 plus x squared? Long division. And it'll fall out almost immediately from that because you'll have a number and then you'll have a remainder and then you'll be able to do arctan. It'll work out pretty clean. Do y'all see that though? I'm not going to work through the rest. This part circled over there, that would become, you know, long division. And oh God, I didn't think about that. No, that's great. That's the way I would do it now. Now that you mention it. Yeah, remember that one? X squared over x squared plus 1 dx and add and subtract 1. Oh yeah, that would work out even better. Because you would split it into 2, right? Right down the middle there. The first one would be a 1 and the other one is negative 1 over x squared plus 1 and that's negative arctangent of, yeah. Look at you. Here you go. I'm going to take the day off. No, I'm just kidding. Yeah. No, that's good. Okay, but not to leave anyone out, the integration by parts was the key to this problem. That part is good to see, but just knowing, I mean, there's no like knowing how to do integration by parts. Who said integration by parts? I heard it. Any reason why? What's that? That's what they kind of look like? Yeah, I mean, you just got to know that, you know, I've got a bat back here and I've got an axe over here, and you just got to pull them out and just go for it, you know? I mean, if you forget that you're holding a certain weapon in your hand, you know what I'm saying? Like, if you forget integration by parts exists, you know, what's the point? The biggest challenge with integration isn't any one of these techniques in particular. It's the fact that in general, when you have an integration problem, and no one tells you what section you're in the book, what do you do? Because every problem requires its own sort of attack, right? Well, that ends our techniques of integration. All right, we are done. Now the book goes on to talk about using technology and computers and all this stuff, and we already know Wolfram Alpha can integrate a lot of more things than we can, right? So I just want you all to keep that in mind, you know, going forward as engineers or whatever it is you're going to do, that, you know, the computer's out there for you to do integrals on, but I'm not going to spend any time showing you how to integrate on Wolfram Alpha, all right? I remember a professor of mine telling me the thing about integrals, it's kind of like if you were to close your eyes and you were to like reach in the bag of all functions and pull out a random function and lay it out in front of everyone, the probability that you could integrate it is 0. I mean, like there's an infinitely many functions, and the ones that we can actually integrate are so few that it's not even measurable how many we could do. I don't know if that makes sense, but yeah, we'll just leave it alone. We'll leave it alone. That's a whole math majors. We'll learn about the 2 types of infinity. There's countable infinite and there's uncountable infinite. The number of functions in there that you can integrate are countable. The ones that you can't are uncountable, and therefore the probability is 0 that you would pull one of those out. So, all right, here we are. So I spent a little time this weekend putting together the notes for today. So keep in mind that all of this is going to be available to you on the web. So don't sit here and be trying to copy everything down, because I'm not, you know, I don't want to look over at you and see you like this, and then I just click to the next page, and you know, I don't want to feel, you know, like sorry for you, you know, like you're halfway done, like shit, man. Okay, so just again, let's pay attention to the concepts here. You can always go back and look at this later. Improper integrals. Okay, up to this point in this class, all the antiderivative has helped us do is to find areas under curves, right? Remember where this all came from. You had a function, little f, and if you could find its antiderivative and plug in the two endpoints, then you could talk about the area under a curve, couldn't you? And we just spent a lot of time figuring out how to determine antiderivatives. So here's the original picture. Now, what if, instead of trying to restrict ourselves to a nice closed interval, going from A to B, and talking about the area under that finite interval there, what if we wanted to look at the area under a curve on an infinite interval? So now our picture looks like this. So I want the area under this curve, but I want you to start at A and then go forever and tell me the area under that. Right? What would your first thought about that be? Your answer would be infinite? Because you're adding up area, right? And you just keep adding more area, like with that picture. It turns out that there's, as we'll see, there's two possibilities. Either it is going to be infinite, which means that the area, when you add it all up, is infinite, or it's not. So even though this is going down in each of these, at the end there, it's getting smaller and smaller. If it gets small fast enough, then we will say it converges to a number, which means that there is a maximum area that it will never go past. Okay? It's a pretty profound concept to think that that's true.
Doesn't it depend on the limit itself?
Well, it's gonna depend on a lot of things. It's gonna depend on the function itself, how fast it's decaying down to zero, a lot of things. But just for now, do you understand the general idea? Finding the area underneath the function forever. Now, you could go the other direction, right? Instead of going from A to infinity, now let's go from negative infinity. So go out to the left forever. So you're looking for the area under here to the left forever. So notice how my integral looks. I didn't point that out in the previous integral. We went from A, right, to infinity. And then on the other one, now we're going from negative infinity to B. You see it? And then why stop? Why ever stop? Why don't you just go both directions forever? The total area under the whole curve forever in both directions. And that means going from negative infinity to positive infinity. All right?
That's not like the odd function.
Well, that particular one, I mean, the way I drew it might look like it, but we don't need any of that for this right now, like odd or even. I think that's what you were talking about. Okay, note, we will call these type 1 improper integrals. In other words, if your interval that you're trying to find the area under, if it includes infinity or negative infinity or both infinity or negative infinity, they're called type 1 improper integrals. And then we're going to also talk about type 2. So here's a definition. All right, so I'm going to kind of point this out here. Look at this first one. We have the integral goes from A to infinity. Now, infinity is a number, isn't it? I mean, it's not a number. It's an idea, right? Infinity is the idea that a number grows bigger and bigger and bigger and bigger, right? So you can never really truly plug infinity into anything, can you? But you can think about what would happen if you plug an infinitely large number into something, right? Yes? So when I define this integral, I can't just plug infinity in and be happy. I have to look at this as a limit, as what's happening as I let a number go to infinity. And what number is it that's going to infinity? It's that upper limit of integration, right? I want to let that upper limit of integration get huge. Now, if that has an answer, okay, if it has an answer, then it's going to be some finite number. All right. Remember with limits, what were the two possibilities with limits? When we take a limit, the limit either exists or it doesn't exist, right? If it exists, your answer is a number. If it doesn't exist, it doesn't exist. Okay, same thing with the other direction. If I go from negative infinity to B, then I have to take a limit. But what part of it's going to infinity? the lower limit of integration this time. And not going to infinity, but going to negative infinity, right? Negative infinity. If we're going that direction, out the left, we have to go to negative infinity, not positive. If the limits exist, then we say the integral converges. So that's a new kind of word that we're going to be using in this class. Convergence. Convergence of an integral means that the answer is a number, all right? Divergence, or saying an integral diverges, says basically that it's infinite, okay? Or that the limit does not exist. Any questions on terminology or anything like that? Also note here that if you want your integral to go from negative infinity to infinity, so in both directions, what you can do is you can split your integral up into two pieces, where you go from negative infinity to a first, then add to that from a to infinity. So it's kind of like if I draw a picture that goes with this, it's like if I want to go underneath this curve in both directions forever, right, and figure out this total area under it, I can just pick some point A, it doesn't matter where it is, A, and I can do one integral that gives me the area out this side, right? That would be from negative infinity to A, and then I can add to that the integral that goes from A out to infinity the other way. So that's what that equals up here is saying. Do y'all see it? And we move on. Here we go, some examples. So I'll do these one at a time, and then I'll come back and grab the next one. So let's do that first one. Integral from 1 to infinity of 1 over x dx. Now, do you all know what 1 over x looks like? If you graph it. That's 1 over x. That's what it looks like. And I want to go from 1, which if you plug 1 in, aren't you at 1? I want to go from here, and I want to go to the right. I want to find that area forever. Do y'all follow me? All right, so by definition, here's what I have to do. This is equal to the limit as t goes to infinity of integral from 1 to t of 1 over x dx. So I'm using the definition of this improper integral now. And now, this is the good news. What's the antiderivative of 1 over x? Natural log x, right? So we don't need a technique of integration. This isn't anything crazy. It's just antiderivative of 1 over x is natural log of x. So we have now limit t goes to infinity, and I'm going to put this in brackets, of natural log of x, right? Natural log of x, evaluated from 1 to t. Remember how we used to do that with the definite integrals? Maybe I'll put this in a different color so it looks like a little, it'll stand out a little more. From 1 to t. Do y'all remember this? When you're trying to find a definite integral, you find the antiderivative, then you plug in the two endpoints, right? No questions? Okay, let's plug in the two endpoints. I'm not going to take my limit yet. So when I plug in my two endpoints, that means I'm going to have something minus something. I'm using that thing, and maybe you've forgotten it. This is capital F of B minus capital F of A. Does that ring a bell? Okay. So I'm going to do natural log of what first? T. And then minus natural log of 1. What is the natural log of 1? 0, right? So I'm left with limit t goes to infinity of natural log of t. And now let t go to infinity, and what do you get? Infinity. Why? What's natural log of, you have to look at what the natural log function is doing. The natural log function looks like this. Right? And as you go off to infinity, that means as you go out to the right, it keeps getting bigger, right? So that function keeps on growing and growing and growing. So as you try and plug in infinity into this, it becomes infinite. Therefore, this integral diverges because it doesn't go to a number, it goes to infinity. Infinity is not a number. That means that the total area under this thing is infinite. So even though that function was diving down, like I showed you here, even though it was diving down over there and getting smaller, it wasn't getting small fast enough. Questions? So let's try something else. Look at the next one. Integral 1 to infinity of 1 over x squared. Yes.
We have to write the statement of this saying that this integral is divergent.
I would be okay with just infinity. Just you should know that that means it diverges. So 1 over x squared, that function, if I were to graph it, looks, I always tell my college algebra class, this is like the volcano function. It looks like this, then the other side's the same thing. Or it kind of looks like a volcano, but it's infinite in the middle. So it's doing the same thing 1 over x was doing, isn't it? It's diving down on the right side, and we want to go from 1 to infinity again. So I want to know what's happening from 1 out here to the right forever. Do you think it's going to diverge? Depends on how fast it's shrinking. That's really what it's all about here. So let me do this. This is going to be, what's the antiderivative? I need to write the limit first. Limit t goes to infinity of integral 1 to t 1 over x squared dx. So what's the antiderivative of 1 over x squared? That's the derivative. You went the wrong way there. Give him that drop slip back. I'm just kidding with you. Sorry, I had to. It was right there. Right, that's x to the negative 2. So when you do the power rule, it's going to be negative 1 x to the negative 1. Yes? So we get limit t goes to infinity of now negative x to the negative 1 evaluated from 1 to t. And now we need to evaluate. Isn't negative x to the negative 1 the same as negative 1 over x? Okay. So this becomes limit t goes to infinity. And now let me plug in. I'm going to have my two pieces here. So plug in t first. Don't you get negative 1 over t? Yeah? What do you get when you plug in 1? Negative 1 over 1, right? So here's where I am. Limit t goes to infinity of negative 1 over t plus 1. Now let t go to infinity. What happens? What happens to this term when t goes to infinity? What's a fixed number divided by a number that's getting huge? It's going to go to 0, right? That goes to 0. And then what's still there? 1. So your answer is 1. The area under that curve is 1. That's weird, right? That means that if you could measure the area under that curve forever, if you could, it would be 1. Now, if you ever stop somewhere, like let's say you go out and you go the integral from 1 to 10, you're going to get an answer, and I can tell you right now it's going to be smaller than 1. And if you go from 1 to 1,000, it's going to be even closer to 1, but not quite 1. If you go to 1 to a billion, trillion, gazillion, it's going to be really close to 1, but not 1. If you could go forever, it would be 1. All right, if you could. We're starting to get into some somewhat, I guess, profound ideas. The idea that you can add something up forever and it be a number. Does that bother anyone? The idea of adding things forever and it being a number? Let me ask you about this. This is completely, it's on topic but off topic. What is, here we go. What's 9/10 plus 9/100 plus 9/1000 plus 9/10,000 plus 9/100,000 forever and ever and ever? It's 0.999 forever, isn't it? So think about this. I'm adding something. 9/10 is something, right? 9/10. So let's say I pour, let's say I have a container. Let's say this holds 1 cup, all right? And I pour in 9/10. Then it's almost full, isn't it? There's my 9/10 in there. Then I pour in 9/100. Is it overfill? So I pour in my 9/100. There's a little more in there. Now I pour in my 9/1000. There's more in there now, right? And I keep doing that forever and ever, following this pattern that I keep on increasing the denominator by 1 0, right? Will the cup ever overfill? So that's where things get a little challenging mentally. Because some people are always like, no, why not? You have to think about the logic behind this. Look, you're telling me each one of these terms is positive, right? Positive, 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 and I'm adding them up. It's a finite vessel. I'm adding something to a finite vessel forever. Why is that not going to eventually overfill? But each one is positive. Do you agree? So if you can only contain so much, if that cup can only hold 1 cup, and I keep adding something, I agree it's getting smaller, but it's something, and I never stop adding that. I keep adding something. Why is it that it will never eventually start overfilling? What? Yeah, but do you understand the logic of, like, someone could argue the other way, that it's not that it won't happen, or that it will, and it's not easy to come to a conclusion. So, what is that? 0.99? That what you said, right? That's 0.999 forever. So 0.99 forever. 0.99 forever. Am I going to fill up that cup? Is it going to overfill? Okay. Is it going to come up a little short? Or is it going to be exactly 1 cup? What do you think? We have 3 things here. Is it going to overfill the cup? Is it going to come up a little short of a cup? Is it going to be exactly a cup? You go forever. What's that? Come up a little short, but you're going to go forever? Exactly a cup?
Forever doesn't exist. Infinity is not a real number.
Okay, pay attention. Y'all might actually like this. 0.99. I'm going to call that x, everyone. All right? Everyone agree with that? If I just say 0.99 is x, is everyone all right with that? Okay. If I multiply both sides of this equation by 10, what happens when you multiply a decimal by 10? What happens to the decimal place? Moves to the right 1 place. So if I multiply both sides by 10, I get 9.999 forever, right? Equals 10x, right? You agree with that? Okay, over here on the side, what's 10x take away x? What's that down here? 9x. Okay, but isn't that the same as writing my 10x that I just had 9.999 forever, and subtracting from it 0.999 forever? What would happen if you take 9.999 forever and subtract 0.999 forever? Those tails kill each other off, right? The 0.999 forever gets killed off by the 0.999 forever, and what's left over there? No, the tails got, right, these tails cut each other off. And what are you left with? 9. So I'm saying 9x equals 9, which means x equals what? 1. 0.999 forever is 1. There is no number between 0.99 forever and 1. They are the same number. Okay? So the idea of adding something forever, like this integral, the idea of going out forever and getting a number, it's one of these things we just have to be able to get our heads around that sort of concept. You know, if you have a function like something obvious like, let's just take a quadratic function like this. And I say, okay, go from, let's say, 1 and then find the area this way forever. What's the obvious answer? What's the total area if I keep going forever? Infinite, right? Infinite. But there are some functions where they start to decay down to 0, and they go down fast enough that it converges to something. And that's what we just got in the previous problem. With the 1 over x squared, where's, no, why'd you do that to me? How many, where's the 1 over x squared? Did I lose it? Yeah, it converged to nothing, I guess. Well, it's got to be somewhere in there. I'll find it later. I don't see anything on that page. I don't see anything there. Man, where did I lose it? I have no idea. I might have lost that page, everyone. Oh well. It's in the video at least. What was the next integral? We had another one to do. Maybe I went. Where the hell is it? There it is. Damn it. Okay. It was hiding. Our answer was 1, right? So the 1 over x squared, it was converging down to 0, it was shrinking down to 0 fast enough to actually make it so that total area was finite. Okay, the next one I want to do is, or I want us to do, oh, this is a good one. Integral from negative infinity to 0 of x e to the x. Integral from negative infinity to 0 of x e to the x dx. Now I'll be very honest with you the way that I do this, all right? Because as a student, I did it with the limit t goes to infinity or whatever, and that's the way I did it until I finally said to myself, I realized that what I'm going to do is take a limit, all right? So I stopped using the limit and I started using infinity almost like a number. And I want you to watch me on this problem. And you're allowed to do this in this class as long as you understand that infinity is actually a limit that you're doing. You're not actually plugging infinity in. It's a limit that you're doing, all right? So let's first integrate this. How are you going to integrate x e to the x? Integration by parts. Good. I don't think anyone said that, but that's what you would do, okay? So who's got their TI-89? Integrate that for me real quick. We're not going to waste time with integrals now, okay? Just assume we can get them eventually. X minus 1 in parentheses. Okay, so is x e to the x minus e to the x. That's the antiderivative. They factored out the e to the x, right? It was x minus 1 times e to the x. Yeah. Yeah, and they factored out. Yeah, they factored out the e to the x. I just distributed it back through. Because if you did integration by parts, you'd probably come up with that. Okay, so that's our antiderivative, right? And now we want to evaluate it from where? Negative infinity to 0. And then I'm going to plug in. So equals minus equals. All right, let's plug 0 in first. 0 times e to the 0. That's just going to be what? 0, right? And then, negative infinity. Oh, wait, hold on. I left out something. Minus e to the 0. Oops, I missed that. Right? That 0, e to the 0 is there. Minus, there's 0, e to the 0, e to the 0. And then the other one will be, what, negative infinity, e to the negative infinity, and then what? Minus e to the negative infinity. Okay, look everyone, this is very, very important that you understand this right now. Let's look at this first one. What is the first one? Negative 1, okay? Because this is all gone, but this right here is 1, so you get minus 1. All right? Now this one. I'll start with the easier of the two. What's e to the negative infinity?
0.
Why?
E, because you can change it to e over infinity, and then infinity goes to infinity.
Change that to 1 over e to the positive infinity, right? That's what you're saying? I don't know if that's what you were saying here.
Yeah, I guess.
Isn't e to a negative number the same as 1 over e to that as a positive number? So this is 1 over e to the infinity. Now this is what I was saying about plugging in infinity. E to the infinity, the idea here is that what you're doing is you're letting the exponent get bigger, right? So what happens to the number down here? E raised to a number that gets bigger. It gets huge, right? What's a fixed number over an infinitely large number going to go to? Goes to 0. Okay? So that goes to 0. So this guy is going to go away to 0. But what about the part that I've waited for here? I have negative infinity here, right? Times, what did we just say e to the negative infinity went to? 0, right? So I've got negative infinity times 0. What the hell's negative infinity times 0? It's an indeterminate form from Cal 1. So you're going to have to use L'Hopital's rule for it. Remember? Okay, so this is where L'Hopital, how many people saw L'Hopital in Cal 1? Okay, if you didn't see, how many people didn't see L'Hopital in Cal 1? That's probably the more important question. Everyone saw L'Hopital? Or everyone's seen L'Hopital before? All right, so watch what I'm going to do here. I'm going to make myself some scratch work on the bottom here. I'm trying to figure this out right now. I'm trying to figure out the limit as x goes to negative infinity of x e to the x. What I've done is I've grabbed just that part that's causing me the problem right there. See that problem right there? That's the part that's tripping me up, right? And it's when I'm plugging negative infinity into it that I'm getting negative infinity times 0. So I'm taking that and making it its own problem, and I'm going to figure out what the hell is happening here. So this is going to, we already said, this is going towards negative infinity times e to the negative infinity, which is headed towards negative infinity times 0. And that's the big question mark, like that's indeterminate. So how can I make this work a little better here for me? I have to make it infinity over infinity or 0 over 0. So I have to turn this into a fraction. So watch me do this. Make a fraction. So I'm going to make it, how about x over, well, you know what? I'll leave the e to the x on top. It doesn't matter which one you use. If I move my x to the denominator it has to become a 1 over x, right? If I take that x here and I want to make a fraction out of it, I have to make it a 1 over x in the bottom so that it's really the same thing. Now let's do a quick little, let's let x go to infinity. What do we get? Or, sorry, x go to negative infinity. This goes to e to the negative infinity over 1 over negative infinity. What does that go to? 0 over 0. That's what I need for L'Hopital's rule. So now I bring in L'Hopital's rule. Here's my little L. Some people use H's. I like to use the L. L'Hopital says you take the derivative of top and then divide that by derivative of bottom. What's the derivative of top? E to the x. What's the derivative of the bottom? Be careful. Negative 1 over x squared. Good. Well, is this helping? Does this help? We get 0 over 0 again, don't we? So we get e to the negative infinity, over 1 over negative infinity squared, which is still infinity, so we still get 0 over 0. Which means we could use L'Hopital again, right? But what's going to happen is it's going to keep on going, right? Because what's going to be happening to the denominator here? It's just going to, that next one will be what, like 1 over x cubed or something like that? Right, the derivative of negative x to the negative 2 would be 2x to negative 3. So yeah, it's going to be, so that didn't work. I'm trying to show you as much trouble as I can in this problem. How about this? Instead of making my fraction, remember I put the 1 over x on the bottom? Why don't we take the e to the x down instead and leave the x on top? Why in the hell would I do that? If I leave the x on top and then take the e to the x down, when I take it down, can I make it e to the negative x? Let's just check it. I go negative infinity over, be careful, what's e to the negative infinity? E to the negative infinity. E to the positive infinity, which is infinity. So what you get here is a negative infinity over infinity. Can you use L'Hopital's rule when you have infinity over infinity? Yes, that's what you need. You need 0 over 0 or infinity over infinity. So that works. So let me use L'Hopital now. What's the derivative of the top? Derivative of the top? 1 over derivative of the bottom. Negative e to the negative x. Now let's plug in. 1 over negative e to the positive infinity, right? Because again, negative is going to be positive. So what is that? What's 1 divided by an infinitely large number? 0. Ah, okay. So that means, way back up here, that this thing that I didn't know what it was, right, is 0. But in no way, shape, or form can you ever do that and just say that like, oh, it's 0, obviously. You have to show it, and sometimes it won't be 0. So now back to the answer here. The answer is equal to, I'm just stick it right over here. What came out of that first part of this? Negative 1. And then out of the second part, minus, they were all zeros, weren't they? 0. So the answer is negative 1. What the hell, negative 1? How do we get a negative area? Right, wasn't that the area under a curve? Wasn't it? Come back to me. Here you go.
He's getting all crazy on this thing.
Well, that's supposed to be a graph of the function.
That's in region 3.
Yeah, you can kind of see here. Let me see.
So is that the reason why it gives you a negative area?
Yes, because the graph is underneath the x-axis, right?
Yeah.
Yeah, that's why. I'm trying to do a quick graph for you to convince you, but all right, there's the graph. We are to the left of the x-axis. We are below the x-axis, right? So it's a negative area. And the area total from 0 out to the left forever is negative 1. So if we looked at it as positive area, we would just say it's 1, but because it's below the x-axis. Okay. Here's what we'll do, because you should probably start looking at some homework. I don't have the homework set yet, so what I'll do is when I post the notes for you online, I'll just email everybody what you should look at out of this section. So we still got a lot to do in this section, so we'll finish up on Wednesday. Then we have spring break. You can go forget everything.